Okay, so now we're going to deal with we'll review a little bit on the previous stuff on basis and dimension independence, and then we'll continue with section 3 of the current chapter on vector spaces, and linear systems. Okay, so let's review what we've done so far. Well, okay, well, we can do maybe the best thing to do with an example. Let's consider our vector space to be P2. That's the space of quadratic polynomials. Okay, so, and the question is, let's say we have a set of vectors, 1 plus x, 1 plus x squared, and 1 plus x squared. Now, are these linearly independent? Okay, well, the way we check for that is to set a linear combination of these to the zero vector, and see if that forces the coefficients to all be zero. So here, what we have to do is to check. We start from this is the test. Okay, a times 1 plus x plus b times 1 plus x squared plus c times 1 plus x squared equals 0, because in P2, this is the zero vector. Okay, and we're thinking of even though these are like polynomials, not column vectors, we're thinking of those vectors because they have those, because this space is a vector space because it has the properties of a vector space. It has those 10 properties. And we say if any space with operations that has these 10 properties is a vector space. So that's why we can call each one of these things vectors. Okay, so then the way we continue with this is to separate out. We have the notion of equality is same polynomials. So we have to see what are the conditions on ABC for the thing on the right to be the zero polynomial. Well, I have to take all the coefficients of each of 1, x, and x squared. So that's going to be a plus b plus c times 1. That's the coefficients of the constant term, plus the coefficients of x, which is going to be a plus c x, plus the coefficients of x squared, which is b plus c, x squared equals 0. And so this polynomial over here is 0 times 1 plus 0 times x plus 0 times x squared. For this to be the same polynomial, we have to have a plus b plus c equals 0, a plus c equals 0, and b plus c equals 0. So that the test for linear independence reduces to a linear system. For which we can write an augmented matrix, coefficients of the A column, coefficients of the last column, right? And then we put the constant terms over here. Now, let's say that the problem, this is an augmented matrix, right? And one of the things in the last assignment was to distinguish between the augmented matrix and the matrix equation for the linear system. Okay, this is so linear system looks like this. I mean, the matrix equation looks like this. Nope, not XYZ, ABC. Right, okay. Now, it's going to turn out that then we're going to solve this And it's going to turn out that if the idea is this, we're going to solve this, and if we can show that this implies that A equals B equals C, then that shows that, that shows that these three vectors are linearly independent. However, if they are linearly independent, it's only going to be one solution, right? So we can see from this, the only possible solution is 0, 0, 0. But if there's only one solution, that means this matrix is going to be invertible, right? So we can actually, we can't really necessarily, we could try to find the inverse and see if it had the inverse, but if it has an inverse, then you could sort of argue, well, there's only one solution, because this would be invertible. I could multiply both sides by the inverse matrix. I still get 0 over here, and I get ABC equals 0. So you could solve this problem using the matrix equation method or the augmented matrix. And but of course, for this problem, this one is simpler because you have to do the inverse. You have to use a giant augmented matrix, and well, that's bigger than the other one. So. One thing that some people did was, in the giant augmented matrix method, you have to apply the row operations to the whole row. You can't just leave the identity matrix that would be on the other side alone and just do the row operations on this one. That was a mistake a few people made. Okay, so let's go and do this. Find the solution to check whether these are linearly independent. Well, we can do minus row 1 plus row 2 to clear off this first one. And we'll have 1, 1, 1, 0, and 0, minus 1, 0, 0, and then that's it. 0, 1, 1, 0. And then we can do row 2 plus row 3 to have 1, 1, 1, 0, 0, minus 1, 0, 0, and then this will be 0, 0, 1, 0, which means that solving these for A, B, and C, you can see that the third equation is C equals 0. Then the second equation is basically minus B equals 0, so B equals 0. And the first equation is A plus B plus C, but since B and C are 0, that's A equals 0. So three vectors are linearly independent, and this, because there's only one solution here, this is going to be an invertible matrix, because this is a linear system with one solution, and so it has no free variables. So that now that's in fact, but that there was a theorem that said, well, if given that's true, I could change this to any numbers over here, and there'll still just be one solution, because if I find the inverse, I can just say ABC will equal the inverse times those numbers. Okay, so there's like a lot of different ways to look at all this stuff. We just found linear independence, and that was the initial ostensible problem here. And you can see that even though we didn't have column vectors to start with, we end up with a linear system, and we could still write this. If we wrote the solution, you could sort of see there's an ambiguity. Well, can't we just write the solution as a set of column vectors? Well, but that's not really the vector space. But there's going to be a connection here, and we're going to get to the connection when we come back to bases. But there's some connection that every vector has a representation in a given basis as a column vector, and we'll use that later on to sort of. That's why we'll be able to treat everything with these spaces, using column vectors. But right now, we'd want to say, if I wanted to know what the solution was, we want to use polynomials in the end. So come back to that, but that's linear independence. And we also had the idea of let's take a space, say P, that equals X, Y, Z, and W, such that X minus Z equals 0 and Z minus W equals 0. Okay, well, there's a vector space. The question is, what's the basis for this vector space? Well, what you do is you have a linear system here, 2 equations and the 4 variables. Well, you can obviously solve for, if I wrote this as a linear system, you'd have X, Y, Z, and W as the columns. And so your equations would be X minus Z equals 0. And the second equation would be Z minus W equals 0. So you can see that the leading variables are X and Z. And so solving these equations to see that X equals Z and Z equals W, Z and W are free. So the goal here is, that's the social convention of what we're doing here. Let me, since I've taken up some horizontal space here, maybe I'll put this down here. So we can write P equals, this thing, we can replace X with Z, and let's see. Oh, Y is also a free variable, right? X and Z are free, Y is free. X and Z are leading. You see something, let me just think about this for a second. Let me get this straight. Okay, so we have Z and W are obvious, not Z. Oh, okay, here. I have blown this. I'm going too quickly, and I can see that I had 2 equations and 4 variables. Okay, so here's my equations, right? Well, it's an echelon. This system is an echelon form, and right. No, it's not an echelon form. That's the whole problem. See, that's what I got myself in trouble by going quickly and seeing, oh, that's an echelon form. But it's not an echelon form because this Z is over this Z, right? So we'd have to, to do that, what we do is we would do a row operation in our chapter 1 kind of way with row 1 plus row 2 to get X minus Z equals 0. And then that would be here. Oh, I can't do that. Wait, this is, what am I doing? I completely lost it, right? Let me just write this down as an augmented matrix to make everything clear. So I've gotten myself in. So here's X minus 1, 0, 0, and the next one is 0, 0, minus 1, 1, minus 1, 0. Okay, and that shows that it is correct that X and Z are leading, and that means that X and Z that is Y and W that are free. Okay. So, but we still have to do back substitution, and that's what I solve for the Z leading in terms of W is free. What I mistakenly classified Z as both leading and free, which led to a nonsense. Okay, so I do back substitution. I solve for Z in terms of Z. Then the first equation, X equals Z, then equals W. So you have you have x equals w. So then you have both x and z in terms of free variables. So coming over then to here, well, y is free, so it just stays there. But and since z is leading, x is leading, and z, okay, so here, that's what I have done. Yeah, that was that over. Okay, so x is the free variable w, y is free, and then z is leading, so z equals w and w. There you are, okay? Y and w. This was, sometimes simple problems turn out not to be so simple if you go quickly. So here's the variables, right? Just to recap, and we have, so just writing the system down in the standard format, it is in echelon form, as this confirms. It helped to write this down to sort of, it was hard to look at this, but then going to the augmented matrix, at least for me, helped me out to see that x and z were leading, and then y and w were free, and then what you have to go through the system, go through back substitution to solve for both z in terms of w and then x in terms of w. So this is the so now what my goal again, apart from this technical thing, was to find a basis for this space, because we want to find, and so first we want to write this as a span, because the first idea is to say find a basis for a space is to find a span. So one is to find a span and then check two whether it's linearly independent. So we're given a space with some constrained by a linear system, so we want to write it now as an unconstrained, and then we can pull it apart and pull out the free variables to see that it's going to be y times 0, 1, 0, 0 plus w times 1, 0, 1, 1, such that y are members of R. So now we've written P as a span, so we can see that these two vectors span the space. So we can choose our candidate basis B, right, as 0, 1, 0, 0 and 1, 0, 1, 1. And then we could, if we check that these were linearly independent, they're almost trivially so, because if I take A times the first one plus B times the second set to 0, because you can't oppose, since every time you have a 1 here, you have a 0 here, every time you have a 1 here, you have a 0 here, that's just going to set those immediately to the coefficients of 0. So this is clearly linearly independent. I mean, you could write it out. I'm just saying it so that, you know, that hopefully that's clear. Okay.
The basis based on the span of P.
Yeah. So we have, so a basis is a set of vectors that spans the space, and by doing this, we've shown that B spans space by construction, because we've just exhibited that it spans the space. Then we've checked intuitively that B is linear independent. So now here's one thing we haven't talked about, which is a little new, is a basis is actually a sequence, not just a set. So I'm going to write, so here is a set of vectors, V1, V2. A sequence, we're going to use angle brackets to indicate that vectors are, a sequence just means they're in order. So for example, from this one, I can get two bases. Basis 1 equals V1 and V2, and basis 2 would be V2, V1, okay? So the difference, so it turns out this has something to do with, if you think back to the connection with coordinate systems, it's sort of like saying, well, I could take X and Y, or I could sort of flip this around and treat it, instead of treating this as XY, flip this around and think of it as a Y X plane. Or think of this Y as first and then X as second, so I'd have, so that there's different coordinate systems I could choose to map out the plane in terms of here, like Y, X. And maybe I'd want to do so, anyway, so there's some connection here between different coordinate systems in these different orders, but a basis is formally a sequence. We want to check linear independence on the set that's underlying the basis. So I can, once you have a set that spans the space is linear independent, you can choose any sequence you want, and that's going to be a basis. Okay. So that's the idea of a basis. It is a set of vectors that spans a vector space and is linearly independent. Okay. Now, the dimension of the space here, dimension of P up here, is the number of vectors in any basis. So here, the dimension of P is going to, since we found one basis, or we found either of these bases, the dimension of P up here is 2. Okay, that's sort of reviews what we've been doing during the last couple of weeks.